coming in and P2 drone coming in. P1 dot P2 is of order S, while P1 squared is M squared. It's negligible, it's 0 in a high energy process. P2 squared is M squared, M2 squared is 0. P1 dot P2 is essentially then what remains in the total P1 plus P2 squared, which is S, the invariant, the well-known S in the hard scattering process, and that's assumed to be large in all of these treatments. So you do have a hard scale and you do have small scales, and the hard scale is much larger than M squared, which means that as far as any hadron is concerned, P, that there is very nice and in a natural way that P is more or less a light-like direction. P squared is 0, which means it is a light-like variable. I don't know how, is everybody familiar with light cone variables, plus and minus? You don't use x0 and x3, otherwise we will sit down this afternoon or so on some occasion with me. You define x0 plus x3 as x plus. I do it x0 plus x3 divided by square root 2, and x0 minus x3 over square root 2 is x minus, which means that x squared is now x plus times x minus, actually 2x plus times x minus, x plus x minus plus x minus x plus, and then if you have transverse directions, minus xt squared or plus xt squared, depending on how you define it, variant xt squared or whatever. So you have it's not x0 squared minus x3 squared, but it's x plus times x minus times x plus. That's how the light cone variables work and how their product works. Now, if you have P, then in any hard process for a given light-like vector P, which corresponds to one of the hadrons coming in or going out, because all hadrons are treated as light-like directions, if you look at P1, there is usually available in the hard process another vector, like P being P primed, which has this property, that it's hard with respect to P. If that's the case, that vector can always be used to define an n vector, which is also light-like, and which is P prime divided by P dot P primed. So this is n, and it has the nice properties that P dot n is 1. Now that's nice, because that's essentially what an n plus vector is. An n plus, that's the vector in the plus direction, and that has in 0, 3 is 1, 1. And then you have an n minus, that's another, the other light cone. I drew these two light cones and these two light cones over here. This is the n plus direction, so it's the 1, 1 direction, and this is the 1, minus 1 direction. Minus 1 in the x3 direction. N plus dot n minus is equal to 1, the inner product. So this light-like vector dotted into that light-like vector is 1, while this still dotted in itself is 0, and plus squared is 0, and n minus squared is 0. So these are light-like basis vectors, if you will. Just like you have the time direction, where then the time direction and 0 squared would be 1. Space-like direction, only in the 3 direction, and 3 squared would be minus 1. And 0 and 3 would be 0, the inner product. The time-like vectors have the property that plus minus is 1, and plus squared and minus squared are 0. And for every vector P, which is treated as a light-like vector in high energy processes, there is an n if the P works or is active in a hard process. This n is essentially one of the other vectors. And that P dot 3 prime will be S. So what you do is you normalize the thing essentially, just that n is essentially P prime over P dot P prime, so you have these nice properties like vectors. Now you might say, yeah, but then P, since this is 1, P has the dimension of energy and n has the dimension of 1 over energy, but who cares? The nice thing of plus and minus direction, so using light cone variables is that going from one frame to the other frame is a trivial business. 0,3 is a hard way of doing it. But you know, gamma, beta, I don't know. Plus and minus is so trivial. A boost, at least a boost in the z direction, brings the plus direction into 5 times the plus direction, and then the minus direction is 1/5 times the minus direction. So alpha n plus goes to alpha n plus, and minus goes to 1 over alpha n minus. So boost is just a multiplication of the plus and the minus direction. So I don't care that one of the directions has dimension and the other not, because you can always get rid of it. I mean, you can take one scale that you like, maybe the proton mass even, maybe the Planck's, I don't know, you take it. The nice thing is that by considering P here, what you immediately can say now, I write my plot momentum in an n plus direction, in one light-like direction, in another light-like direction, and then whatever is left. Because there's in principle 4 components in this integration. That's going to be important in TMDs. The one direction I call the fraction alone P, I call that x. If you don't like this dimension, let's divide this by P dot n. I don't care, then P dot n is divided out. I chose it one. And then the n is essentially the n factor. And now what you see is that x, that this is dimensionless, this has dimension of energy, this is dimension 1 over energy, so this has dimension sigma. Now this is at least as a dimension. Now if you use it in a high energy process, sit in a frame where this is high, then this is proportional to Q, this is proportional to the mass of the object, P squared, which is m squared, so it's order 1, and this is order m squared over Q. Just do it, calculate what x is in such an expansion. X is P plus is P dot n, and sigma is P minus is P dot P minus x m squared, and it's order m squared. P dot P, the quark momentum, and the nuclear momentum are part of the same blob. And a blob is essentially, by definition, everything in a blob should be in one direction. Should be in the minus direction or the plus direction. See, that's the hand waving. So such a blob should exist. I mean, it's not evident that QCD would give rise to jets, but it does. So I use the fact that sort of there is confinement, that all the transverse directions are limited to a certain scale. That's something that I can prove. That's sort of secretly used all the time. So then that's this thing, then so this expansion, which is called the Sudakov expansion, and that's essentially what it is. And now you say in a particular frame, this is order Q, this is order M, this is order M squared over Q, I do the calculation, but since everything is written in a covariant way, if I know that in one frame this is the dominant thing, it will be the dominant thing in all frames. So this is now you have to think about that statement, but this is true in this case. And so essentially, if sufficiently high energies, this is the only relevant thing of the expansion in P, it's x times the momentum. The next step, it might be important sometimes to include PT, that's the TMT thing, TMD thing, which I will come to tomorrow in more detail, and then this thing is negligible, but being negligible, ultimately it tells you you have to integrate over it. And with that I'll end, I'll show the next thing, which I'll come to tomorrow.
The m is the mass of the proton?
The m is the mass of the proton. So that's if you want like one scale, and then the other scale, the p, is if you want square root s, and then you see that the third one is irrelevant. And this is what, because you anyway, everything, all the information of the proton needs the rest of the process to go into a physical observable. That's why the expansion in P, N, and PT is a relevant thing, and the orders, the consecutive orders are kept. Now let me, by adding say, and then starting tomorrow with this tells you that this Fourier transform, which I use to define this object, is essentially this matrix element. In principle, it has 4 momentum. It depends on all 4 components, x, pt, and p minus. But this thing is, if you want, becoming irrelevant, so you integrate over it. Then things will become dependent on this n direction. but you have a Fourier transform which has one step less because P dot this direction is not relevant and is integrated out. So what you are left with is this dependence, one variable less, only x and pt. This is the P minus integration. In a hard process you can do it, and it's beautiful because the thing now is at, the thing you integrated over, because this doesn't depend on it, so you integrate over one of the components, which is this is the sign minus, so you integrate over the sign plus, but the integral over psi plus, if you do this thing doesn't depend on it, is essentially just a delta function. So you have the non-locality is now at psi plus equals 0, which is along a light front, not a light cone. So psi t is not yet 0. If you would integrate also over pt, which usually is done, and you get your collinear functions, all the functions that Chunzo is talking about, so you are talking about this level, you integrate one step further, and essentially psi dot n and psi t are both 0, which essentially implies in light-like coordinates that psi squared is 0. So this is a light cone correlator, and it's the light cone correlator which determines the collinear PDFs, and it is the light front correlator which determines the TMDs. But TMDs are already, you might say, yeah, but this thing ultimately in any scattering process, what about time ordering? Now, this is a particular way of defining time. So this is at time equals 0. And so time ordering is no longer important already at this level. And this thing is used in ZPDs, this thing is used in TMDs. These things are, time ordering is no longer relevant, which means you can take these things and I'll set all the theorists here, go to the other room and work with this thing and can talk later on to the experimentalists, because this is a shot of the nucleus. I mean, it's a shot at fixed time and it's relevant in hard processes. So that's the nice thing already of TMDs. And then TMDs are much richer than these because they do have one additional variable. And that's what I got to tomorrow, this richness of TMDs. And if you integrate these things one step further, you have local matrix elements, and then every theorist is happy because local operators, they can be used, and you can calculate anomalous dimensions and whatever. And that's why operator product expansion is so important. These things everybody can calculate, but these things can be expanded in local operators. Because this is around psi squared equals 0, so you can make an expansion of the non-locality. Yet you can also do that here. You will have to go one step further. But of course, you can see already from here to there are problems. From here to there will be more problems. Those problems I will outline, and most of those problems will be outlined on Thursday. So tomorrow the richness, and Thursday the problems. Okay, thanks. And otherwise this afternoon or whatever, afterwards.
Okay, so no student X, I can measure X. One question for student. And the student probably notice that all this property here actually is not gauge invariant, right? I'm waiting for someone to ask this question. But definitely you will explain the gauge invariance.
It's one of the problems, yes.
Yeah.
No, it's that actually already tomorrow we will get. And the answer is for you, you know the answer. Who knows the answer? We put in gauge links in between. And gauge links, where do they come from? They come from these psi A psi matrix elements. So you have psi A psi. But if psi A psi is allowed for one of the A's, for the components with a plus, then the 2 is also allowed, and it's 3 and 4 or 5. And you have to resum them, and they give you an exponential. And that exponential is the gauge link. And so that problem is solved. So I save a lot of time. No, but I'll come to that problem, because this problem is even harder over here. And it's easy over here, it's hard. Thanks for drawing the attention to it. Other questions?
Could you say more about the time modeling part?
Yeah. Let me start off with tomorrow, because otherwise I take away too much time and lunch for the other speaker. I will, as I said, I will come back to this, and I will say somewhat more about time modeling the things. The paper to look at is Deal Bousset and very old papers of Bob Jeffrey on deep and elastic scattering that show that discuss these things. And Deal and Bousset did it for also GPDs, showed that it can be generalized essentially not only at this level, but also at that level. And in the Verena lectures there's references to Deal and Bousset. But I'll discuss that in more detail then tomorrow. So answer that questions. Other things that I should start off with tomorrow, then let me know.
Question was good. Oh, now let's speak again. And let's go to the lobby for